Thank you very much for the kind invitation. As a physicist, it's really a unique opportunity to be able to give a talk to computer scientists at such a great conference for you. And I'm glad that you want to learn about quantum computation. And in particular, quantum computation, people have been thinking about it for over 30, 35 years now, because it's a possibility to use nature in a new way to store and manipulate information that indeed could be much more powerful for certain problems than using classical information, which is what all computers are based on these days. And in particular, people have been talking about a quantum computer could be very, very powerful, and more powerful than the classical computer, exponentially more powerful. And we thought in the last few years that it would be nice to actually do a demonstration to show the power of a quantum computer, even for just any problem at all, even for a crafted problem, just to show that it's possible to do that as a stepping stone to eventually do some useful algorithms. And that's what the quantum supremacy experiment does. And I'll describe that today, and you kind of talk about how the devices work and how we show this. So in order to do that, we have to build new devices. We've been working on it for many decades now, but there's some new ideas here in how to build these devices. And then this quantum supremacy experiment, we basically ran the quantum computer for something like 200 seconds, few minutes. And then to check that, it would have taken thousands of years. So you can see the discrepancy between the power. The basic reason this works is we do a computation on a parallel computation on a huge state space called a Hilbert space of about 10 to the 16. And one of the reasons this worked was that the errors that we always get in a quantum computer were quite low. And in fact, we're very consistent with what we expected from the device doing more simple measurements. And the good news here is that there's no additional bad decoherence physics, things that go wrong when we scale the device. So it gives us a lot of hope that as we investigate more and more on this technology, there's nothing fundamental blocking us. So you still have to worry about practical things, but it looks really good for moving ahead and making more and more powerful devices. So the first thing I like to do in these talks general talks, is to talk about where does the power come from. And normally everyone knows that you store information in bits that could be a 0 or 1. And what happens in a quantum computer is you can store information in quantum bits that can be in a quantum state that's basically in the state of 0 and 1 at the same time. And quantum mechanics allows you to do that. And computationally, what this means, if you want to go ahead and do a computation on this qubit, you can find the answer for what happens for the 0 case and what happens to the 1 case at the same time in this quantum superposition of the qubit. And it's nice, you do a parallel computation here. You're essentially computing 2 states at once, 0 and 1. And that's nice, but of course, well, it's only a factor of 2. So yeah, how practical could that be? But the real interest comes when you start adding more qubits to the system. For example, with 2 qubits, you're doing a parallel computation, if you like, on 4 states, 0, 0, 0, 1, 1, 0, 1, 1. And you've doubled the number of states. And if you look at 3 qubits, it's now 8 states, 8 possible combinations. You're doing a parallel computation, 4 qubits, 16, 532. And you see that the number of states are growing as 2 to the number of qubits, or an exponential growth in the amount of, let's say, parallel computation you're doing. And of course, an exponential growth is really exciting if you're thinking about doing powerful computation, because typical classical computation, the power just scales linearly with the number of bits or speed or resources in some way. And what this means is by the time you're up to 50 qubits or so, which we'll talk about today, 2 to the 50 is a huge number. And basically you can start competing against the supercomputer. And then by the time you get to say 300 qubits, which is something we hope to do in the foreseeable future, 2 to the 300 is a number bigger than the number of atoms in the universe, okay? And that's clearly would be some kind of parallel computing that you can't do ever classically, okay? Now, given all that, you say problem, the constraint here is you have to go measure these states. And when you measure the state, you only get n bits of information, 50 or 300 bits. You don't get all this parallel information. And what that means is when you run a quantum algorithm, you kind of get a minimal amount of information coming out of the quantum computer. And thus you have to carefully design your algorithms in order to extract a useful answer from that minimal amount of measurement. Even though you're doing a parallel computation, you get a small amount of information. But there are algorithms that you can do where that's a useful way to use it. You just can't run any classical calculation and expect to get this exponential speed up. Now, I'm going to talk a little bit about how we did it and the hardware today. And of course, there's a lot of people around the world who are trying to build it using traditional atom systems, such as electron spins or atoms where they're atomic clocks and you look at the states here. And what we're doing here is actually doing something for a new kind of atom that was only really looked at and understood how to do in the last few decades. And that's we're making atomics, quantum systems out of electrical circuits. And what happens is in these electrical circuits, the current and voltages, which represent the collective behavior of many, many electrons in the electrical circuits, it's that collective behavior of the current and voltage that's quantum mechanical. So instead of currents and voltage being a classical quantity in a normal circuit, normal electrical circuit, it's quantum mechanical. And the nice thing here is because it's a macroscopic system made out of electrical circuit, and you can see here there's a picture, it's about a fraction of a millimeter across. Here it's aluminum circuit, which is the tan, and the dark brown are insulators, breaks in the aluminum circuit. It's macroscopic, it's easy to control. You can bring in wires from the right or left to control this circuit. And thus you can build a complex circuit. It has engineered properties so that you can use standard microwave engineering to understand a lot of the device. And of course, the big thing, it's built like a computer chip. So once you make one, you know how to make many, and then you can scale it up in a similar way. The way that this circuit works, the way the quantum mechanics works, is it just builds an inductor capacitor oscillator, if you like. And in this case, what happens is the island here given in blue and the ground plane around it form a capacitor of this oscillator. And then these two Josephson junctions at the bottom, which are just two crossed aluminum wires with aluminum oxide in between, forming a tunnel junction so that the electrons can tunnel through, that forms what's called a Josephson junction, which is basically a nonlinear inductor. And the inductor capacitor forms a resonance at about 5 gigahertz, and then you can store and manipulate the quantum states in that. So this particular system actually maps very well, perfectly to a pendulum, okay? And the zero state is just the ground state of the system. Semi-classically is just there's no energy in the system. And then the one state is the first excited excitation where there's one microwave photon in the system. And if you know about quantum mechanics, you can draw some wave function to that and use kind of standard quantum mechanics to understand what's going on here. And then the other thing we do is we have a little loop here with a wire coming into here that puts magnetic flux in this loop. That loop changes this inductance and changes the frequency of this oscillation, which we use to control the qubit in a more complex way. So here's an example of a very simple quantum calculation we can do on 1 qubit. We initially just let the whole system relax to the ground state. And then what we do is we put on a microwave tone to this, injecting microwave current into the circuit that's resonant with this oscillation. And then you'll make a transition from the 0 state to the 1 state as the oscillator just absorbs the on-resonance oscillation. Now, because it's a nonlinear circuit, you make a transition from 0 to 1, but then if you give it more time, you start making transition from the 1 state to the 0 state. So if you put on the microwaves for a certain amount of time and then measure it, as quantum mechanically, you get a 0 or 1, but what you do is you measure it 1,000 or 10,000 times or so, and you get a probability of 0 and 1. And if you plot that probability of, say, the 0 state versus the time that the microwaves are on, you start in the 0 state, and then it oscillates first to the 1 state as a 0 to 1 transition, and then it oscillates back to the 0 state from a 1, 0. And it goes back and forth between 0 and 1 in this cosinusoidal oscillation. This is called Rabi oscillations. Now, in terms of doing logic, as you would for a computer, you can imagine that if you pulse this microwaves here for 20 nanoseconds, that turns a 0 state to a 1 state. And if you're in the 1 state and you pulse it for 20 nanoseconds, that takes it from a 1 state back to a 0 state. So a 20 nanosecond pulse is equivalent to a NOT gate, like you know for classical, computer hardware kind of logic. So it does mimic classical behavior. However, if you pulse it instead of 20 nanoseconds for 10 nanoseconds, you then take the 0 state into the 0 plus 1 state, which is the superposition state I talked about before. And then if that state, another 10 nanoseconds, that'll take you into the 1 state. And what you can do is represent this 10 nanosecond pulse here as a square root of naught. Just like a naught and naught is identity, a square root of naught is a NOT gate. And that's what gives you these interesting quantum states. And what's nice here is that you have a set of self-consistent logic like you do for classical logic, but now you have these additional strange quantum operations like square root of naught that enable you to use and manipulate the states in a more powerful way. And then, of course, you have to build algorithms based on that kind of thing. So think of it as having a bigger instruction set for the basic operations from quantum mechanics, and that gives you the power to solve these problems in this more complicated way. Okay. So this is for 1 qubit. Of course, just like a regular qubit, you need a lot of bits, you need a lot of qubits. For this particular, we scaled up the device to 54 qubits. And the little crosses, gray crosses here are the qubits. And then they're connected to each other in this rectangular array with these blue boxes here, which are adjustable couplers that allows 1 qubit to talk and exchange energy with the neighboring qubit in an electrically adjustable way, so that we can control and make all the gates that we need for a logic operation. And the nice thing here is with this 4 nearest neighbor, that gives us good enough connectivity to run algorithms, and also it's forward compatible for surface code error correction and other things you want to do in the far future. So this is a very good milestone experiment for that. And this is the particular chip we made. The bottom chip here, you can see bond pads around the outside, which brings wires into the center of this. We have a second chip on top of that that's indium bump bonded to the bottom chip. And this second chip, it has all the qubits in it. And these wires just control the qubits. And this is a few centimeters across, so it's not a large chip at all. And then we take that and we put that into a microwave package where we bring those, with wire bonds, we bring that out to an array of microwave connectors, put this into a thermal grounded circuit, And then we connect that into this instrument here, which is called a dilution refrigerator, which connects up all these wires to room temperature control electronics and connects the output of the circuit to quantum limited microwave amplifiers in order to read out the device. So this device is operating at about 5 gigahertz, which is convenient. It's a microwave frequency that's easy to work with. But in order to have the quantum energy, which is Planck's constant times 5 gigahertz, to be greater than the thermal energy, which is the thermal energy will scramble the bits and make it not work right, at 5 gigahertz, you have to operate this at very low temperatures. So this is operated at about 20 thousandths of a Kelvin. So it's 1/10,000th of room temperature. So that sounds very difficult and hard, but people have been making dilution refrigerators for many years, and it's just something you buy, and then you get into this usable temperature and frequency regime in which you can measure these qubit devices. And then at the top, all these wires go to rack of electronics. These are custom built gigahertz generators based basically on cell phone A to D and D to A things. So this is, in fact, because of that technology, and this is not too expensive to build. It's still a little brute force at this point, but you can do all that and control the system. And of course, behind this is a tremendous amount of software to control the device properly. I'm going to go into this very briefly on a little bit more detail. I said the adjustable coupler was important and new. Here we have the qubits, as I talked before. These are just nonlinear inductor capacitor resonators. And to couple the qubits together, we build another inductor capacitor resonator. But this particular kind of qubit, if you like, is at a higher frequency than a regular qubit. So then when this is oscillating at 5 gigahertz, this is off resonant oscillating a little bit, and then which drives the other qubit. And the amount of drive from one qubit to the other depends on whether the central control qubit is close in frequency to the qubit where the net drive is strong, or far away in frequency where the net drive goes down. So you can adjust the amount of coupling between the two qubits with adjusting the frequency of the center one. And it turns out that this net coupling looks like a negative capacitance. So if you add a physical capacitance between that, then at a certain frequency here, those two capacitances will add to zero, and you get zero coupling and you turn it off. So you can turn on and off the coupling and perform logic gates as you want between two qubits. And for example, if you know about classical logic, this is like building an AND gate. Once you have an AND gate and a NOT gate, you can build any classical logic. Having this kind of coupling and the NOT gate I showed before allows you to do any kind of algorithm that you want. And this is just an experiment to the left here showing how it works. We have two qubits and we put a NOT gate onto it. So we put a 1 state here and a 0 state here. And then what we do is we change the frequencies of the qubits, and we turn on the coupling so that this excitation will swap from one qubit to the other. And then at the end, we measure it. And this is the data, let's say at 0 coupler bias in here. You see this population transfer from 0 to 1, goes from no transfer to transfer, no transfer to transfer. It oscillates back and forth as the quantum information is sloshing back and forth, doing its gate operation. And then if we adjust the coupler bias so that it's a little bit lower in frequency, then at some point that oscillation just completely disappears, and that when it's turned off. And then we can turn it back on again, actually quite strongly, by bringing this coupler bias. So basically, with the current flowing through this wire to this qubit right here, we can go to an off situation where the qubits are isolated, to an on situation where they're talking together and doing a logic gate and doing a quantum computation. Okay, so we have basically like an AND gate. It's more like an XOR gate, but it's some kind of 2 qubit gate and single qubit gates, and then we can perform an arbitrary calculation. Okay, so I'm going to talk a little bit about the quantum computation we do more in general. But at first, what I want to do is talk a little bit about some careful calibrations we have to do. When you run quantum bits, they are fundamentally have errors in it. Classical bits have extremely low error rates. Most cases, the error rates are so close to zero, you don't have to worry about it. In quantum computation, it's an inherently fragile state. Quantum mechanics just forces that to happen. And that means if you want to make a good quantum computer, you have to worry about the error rates. You have to make them small. And in the end, you have to do error correction so that these error rates can be exponentially small. Now, part of this is designing these qubits to have low error rates. And here, I want to show you what the measurement of those error rates, because we're going to need to use this later to test the full quantum computer. So what happens is we'll take an isolated qubit, we'll turn off the couplers between them, we'll bring all the other qubits way far off resonance so they're not going to talk to each other. This is doubly turning them off. And then we do these square root of naught and naught operations and see what happens. And what happens is this envelope decays over time because of the because of these errors. And what happens is you basically can run about 500,000 operations or so before you lose the state and you lose the coherence due to errors. And you measure this very carefully, this decay of the state. And from that, and measuring versus a number of operations from 100 to 1,000, you can get an error per gate. And that error per gate is something like about 0.15% for these qubits. So you measure this on all the array separately of all of them, and then you get some histogram. And what I do here is I integrate to get that histogram because there's a smallish number of qubits, and then you get a characteristic of the performance of the device. So this is kind of a little bit of stretched Gaussian here. And you see the average or the mean error is about 0.15%. So 600 operations or so, and then you lose the qubit state. And some are a little bit better and some are a little bit worse. Okay.
And just to clarify, so you're actually, when you take your device, you're calibrating each junction or each qubit?
We're calibrating, in this case, each qubit, and then we go from qubit to qubit to get the histogram. Some are better, some are worse. Now, the important thing here is we're doing them one at a time. But if you're going to operate something like a real computer or a real chip in your phone, for example, you're operating all the transistors at the time. You're doing it simultaneously. So what we then do is a more complicated experiment where we're turning off the couplers, but now we're doing this measurement of how the qubit loses its state on each one simultaneously. Just like, you're operating your transistors in your CMOS. And in that case, you see the decay. And then in there, you see the black line here as opposed to the dotted line. And okay, it's a little bit worse. Expect some crosstalk and things that not work quite so perfectly. But what you find is that it gets worse only by a small amount or so. You go from 0.15% to 1.6%. And that's really good. It means that you can operate these simultaneously. Okay, so you do the same thing for the 2 qubit gates where they're swapping back and forth. You take 2 isolated qubits and you measure them here. And that's about 0.36%. It's a little bit worse because there's 2 of them, but not that worse. And now you do it simultaneously where you're doing pairs across the whole array. And in that case, it gets a little bit more significantly, goes from 0.36 to 0.62. So it's a little bit more sensitive to crosstalk in this situation, but it's still good enough that you can do algorithms. And it's something you want to work on, but it's at least not so bad. You do that with measurement. And from this, you basically are getting a map of how the operations are working, how the qubits are operating, how good they are in a practical sense and simultaneous. Now, of course, these are things just doing single or pairwise. And what you wonder is, what's the performance when you're running all the transistors simultaneously as you are in your CMOS chip? And that, in fact, is what the quantum supremacy in some sense is about, is to say, well, how good is this whole device going to work as you work? And is it going to degrade, or is it going to still work okay? You need to do that experiment. Just like you want to know, you can calibrate individual transistors, but you want to know if your instruction set still works when you run the complex thing. So that's what we're going to do in this experiment. Now, one thing I would like to say is, because you can have a knot and square root of knot in a continuous, power law of the NOT gate. It's a continuous, it's an analog computer. Calibration is super important to get things right. And this is an example of a calibration graph for doing the qubits, all these different experiments that you have to do. Just to give you an idea of the complexity, these two dots are the PhD thesis of one of my students back at UCSB. And he spent, many years trying to figure out how to get that right. Once you understand the physics, you write the code, you put it into Python code base, and then you build all this and more calibration procedures to automatically do this. So there's really a lot of things you have to do to get it to work. But fortunately, in the end, once you understand what's going on, you just turn it into software, just software. But of course, that's the big part of getting the experiment to work. Okay, so at this point, let's talk a little bit about how to run a full quantum computer algorithm. And this is the array of, it turns out, 53 qubits. And when I have a single circuit, that's a 1 qubit gate, say a square root of NOT gate or a NOT gate. And when I have a line between them, that's this swapping operation that I was talking about. And it turns out that what we do is we do an algorithm where we do interleave single qubit gates with 2 qubit gates, with the 2 qubit gates rotating around one particular qubit to connect to all its nearest neighbors. And it turns out that that particular sequence allows you to run a general purpose algorithm. Whatever algorithm you want to run, you can, of course, put it into this kind of sequence that you want. And of course, you do simultaneous gates on all qubits. So here's the bottom of that circuit. We're just looking at one interior qubit. And this is actually the sequence we use for this quantum supremacy experiment, where we do a single qubit gate, which are these square root of NOT gates. Okay, but now we have 3 kind of square root of NOT gates. There's one square root of NOT gate, one at which we change the phase by 90 degrees, and one which we change the phase by 45 degrees. And the phase is a very important part of these algorithms. These particular square root of NOT gates are known but randomly chosen. That's part of the algorithm. And then we run these 2 qubit kind of swapping operations, where we more or less do a square root of swap operation. And then we just interleave this back and forth with a random choosing of the single qubit gates and this known 2 qubit gates. And we run that for a number of cycles, typically 15 to 20 or so cycles. And then we do a measurement at the end of the qubit states. And these single qubit gates are about 25 nanoseconds in length, and the 2 qubit gates are about 12 nanoseconds in length. So these are tens of nanoseconds per cycle. The coherence time is about 20 microseconds. So we can do many operations before we lose the coherence of the device. And of course, we'll be looking at that. So the quantum supremacy experiment is using these randomly chosen NOT gates, square root of NOT gates. And you can think of this as a quantum pseudo-random number generator, okay, where we create this very complex states with all the possible combinations of the qubit states, as I talked about earlier, in a very complex way. And then at the end, we measure the qubit and we get what looks like a random 0 and 1 combination of all the 53 possible 0 and 1 states. Okay, so it looks like a random number generator. And given that you're doing all these random operations, your classical kind of normal intuition is that all the possible states are possible. And you would expect them to have a probability of every state to be 1 over 2 to the n. So that's kind of your classical intuition for this such a random number generator. But in fact, what happens is we see something that we call qubit speckle. And this is analogous to laser speckle, where you take a coherent laser beam, you shine it through frosted glass that diffuses out. And in some directions, the coherent laser beam adds an amplitude and you get a bright spot. And in some directions, the coherent beam subtracts from each other and you get 0 and you get a dark spot. So some directions are bright and some directions are dim because of the coherence of the light. It's oscillating together everywhere. Now, the same thing happens with the qubits, where that on average, it's 1 over 2 to the n of probability of all the states. Some states have constructive interference and are brighter or have a higher probability, and some states are dimmer and have a lower probability. And in fact, the check with the quantum supremacy experiment is that when you sample these huge number of states, are you measuring the bright ones? You should be measuring the bright ones and not the dim ones. You should be measuring the high probability states. And the way we check that is we take this circuit and we run it through the quantum computer and we get some output states, a series of zeros and ones. And then we take the same calibrated circuit, carefully calibrated, and we run it through a computer or a supercomputer, in fact. And then you compute the probability of all the states, which has this speckle in it. And then you check whether the ones that you measure were the bright ones. And the way you do that is this very simple formula where that takes the ones you measured, and then you you look up what the probability was. And if it's randomly chosen, the probability is 1 over 2 to the n, this fidelity is 0. But if it's the bright one, it's bigger than 1 over 2 to the n, and the fidelity is non-zero. And in fact, if it's a perfect match, you will get a fidelity as 1. And if there's no match at all, it's 0. And in fact, if there's any error at all in the circuit, if you had a bit flip or you had the phase that flipped by 180 degrees, then it'll go to 0. So it's actually a very nice way to measure, did you get 0 errors when you ran your circuit, or did you get 1 or more errors when you ran the circuit? And thus you can quantify how well the circuit is working. And this is, actually quite useful in terms of experimentalists to calibrate whether your machine is working properly. So here's the data for the quantum supremacy experiment. And what we have here is this cross-entropy fidelity on a log scale, with the top being 1 if it's perfect. This is versus the number of qubits. And this is for 14 cycles. So there's 14 2-qubit operations and there's 15 single qubit operations with this square root of naught of different phases, okay? And let's first concentrate on the red circle, which is the full circuit. And here at 12 qubits, we're looking at a small part of the array. And in this 14 cycles, that's about 250 total gates. And given that we could do 500 or 1,000 total operations, it's maybe not surprising that at 250 gates, we're not getting unit fidelity, but it's roughly around 50–40%. So, a decent amount of time, there were no errors and you get the right answer, okay? And then what you do is you just do the experiment on a bigger and bigger parts of the array, starting from 12 and going up all the way to the total number we had working, 53. And as you use more and more qubits, there are more gates, there's more chance of an error, and the fidelity goes down. And in fact, it goes down exponentially as you expect in this smooth way. And you can see there's data going out here all the way to 53 qubits. Now, from about 12 to about 30 qubits, you can solve this problem on a laptop. But once you get beyond that, remember the amount of computation that's going on, the number of states is growing exponentially. So by the time you get to 30 or 40 something or so, that's a lot of states, that's a lot of memory you need, and that's a lot of computation you need. So you have to start doing it in a workstation. And then finally at 53 qubits, this is more or less 5 hours on a supercomputer, on a either on a data center or a supercomputer. And it's quite expensive, but you can still check it, right? You can only get the red circles if you can run it on that. Now, the other thing you can do, you're worried about this taking so long to classically verify it. You can do a simpler circuit. Here, let's just take the patch circuit where we take this array and we just remove all the 2-qubit gates in between the left and right-hand side. So now these 2-qubit arrays are working independently, and it's exponentially easier to simulate that. You just simulate one and the other, which are way easier, and then you get the total answer. And because the amount of gates that you're running is more or less the same as before, when you look at the data, it's more or less lying on top of the red circles, which is kind of, which is what you expect. I'll explain this a little bit more later, but you can check. And then you can do something in between where you just take out some of the gates, and there's a fancy algorithm to do that. And then you get the green crosses. So all these things kind of make sense, and you can check that. Now, one of the reasons we were able to use this is this particular gate sequence that we used. There was a mathematical trick to simplify the calculation. If you change the gate sequence just slightly here, it then becomes way harder to calculate. And now instead of 5 hours, it will take you weeks or years or millennia to do the calculation. And in fact, there's no red circles here because we couldn't do the calculations to check the data. We've archived it. If someone invents an algorithm, they can check it, but we couldn't check that. And that's the quantum supremacy regime, of course. However, you may wonder, is the thing still working right? And what we do is then go to the patch and elided circuits, which we had used here as a proxy to the red circles. We can do those circles, take the data, and that's given here with 5 sigma error bars. And then we expect the red circles to lie on top of that. And since the red circles are quite significantly different than 0, which would be if the quantum computer wasn't working at all, we then can claim the quantum supremacy that things are working properly. Again, we have the data set if one wants to check that. So that's the thing. We're taking data with 200 seconds, and we've taken data that would take a long, long time to check if you could do so. Okay. So given this, I want to talk a little bit about the interesting quantum science and also what this means in terms of building a powerful computation machine, okay? And one of the interesting things here is we achieve the same fidelity, basically the same performance of running the whole quantum computer at once, whether we did a full circuit or a patch circuit or a elided circuit, which basically means that the errors did not depend on the amount of quantum entanglement, and more importantly, the amount of computational complexity of the machine. And that's really good because in the end, we want to do very computationally complex, and it means that the errors are not going to blow up for some reason because of computational complexity. The fact that we assume computational complexity theoretically is good. The second thing I want to do is go back and point out this black line here. And this black line was the prediction from the slide I showed you earlier for the single qubit errors and the 2-qubit errors and the measurement errors that I showed you. And what's very nice about this is we just do a very simple calibration of the device, and then we run this very complex algorithm. And we can predict the performance of the complex algorithm from the simple kind of base unit error rates of the system. And that's very good because you want to be able to predict your errors and understand the physics. And it turns out the prediction is basically a classical probability prediction based on high school probability, okay? Where we have an error rate and we have a fidelity per operation of every single and 2 qubit, and we just multiply all those probability fidelities together to get the net fidelity. It's the simplest thing that you can imagine. Now, you expect this from quantum mechanics if, all of these proper assumptions are made. But of course, you want to do an experiment to show that there's not any weird correlations. So it's very interesting here that in terms of calculation, you have to calculate it using the amplitudes of the quantum states, and you get all this interesting coherence effects that allows it to be possible. But in terms of errors, you can think of it in terms of classical probabilities if things are done right. And that, of course, that's the assumption behind it. It's good that we showed that. And it shows you kind of there's really something interesting about these quantum calculations. You should be able to use them to do a calculation. Finally, I would just say the quantum works for this 2 to the 53 or 10 to the 16 Hilbert space. This was previously tested to something like 1,000. So now we're really at a powerful limit here, and everything is still working properly. So that's very, very good. Just to say, once you build this quantum computer, you can start doing things with it. One of the algorithms types that are very interesting is doing quantum chemistry on it, where you map a chemistry problem of how a molecule binds together to a quantum computer. And then quantum chemistry is typically hard because there's an exponential number of state spaces. And because you can map this to a quantum computer with that power, you expect it to solve problems. So here's a simple algorithm between 6 and 12 qubits. And then it's kind of looks like the hydrogen dissociation curve. As you move the distances between the hydrogen atoms, you get some binding curve. And you can find some algorithm and run the experiment and show that things are working properly. So this is double the numbers of qubits. Electrons is prior chemistry simulation, so it took it forward, and more than 10 times the number of gates. And the nice thing here is to do this kind of thing, we have the Sycamore chip, we have the hardware, there's an open source Circ programming language to do that, and then there's an open source program that can convert your quantum chemistry to a qubit language. So we have a full stack solution for using these kind of devices to start doing actual quantum computation. There's some other software available too for other kind of calculations. So this is nice. We're building an ecosystem for that. And eventually Google will want to have a cloud offering for doing this. And we've looked at other things besides this quantum chemistry, adiabatic optimization, Fermi-Hubbard model. The thing that I would like to point out here is the total number of gates that we're doing in these simulations are into the hundreds of thousands, which means you can actually run pretty complex algorithms at this point to see how the quantum computer is doing. Most of these algorithms, you can still solve them. All these algorithms, you can solve them classically. So we're not powerful yet for most of them, but they are a large number of operations. So you can test your algorithms on a realistic depth circuit to see how they're working, and learn more about running algorithms in this way. So we're really entering an interesting era. So at this point, let me just conclude here, give a summary. These complex quantum computers work as expected on these huge Hilbert spaces where you can get into a powerful regime for this one crafted problem of a random number generator and sampling. The physics looks very good. Of course, we want to go from just showing the power of a quantum computer to do something useful and powerful. And that's the next step. And that's a big step. It's not like it's going to come right away. And people, to get there, they're working on the hardware end to make the hardware improved and lower errors. And they're also working on the algorithms to see if they can make the algorithms smaller and smaller so that they can eventually merge. Whether this will happen in the next few years or maybe 10 years or more when you do error correction, we don't know yet, but people are working to do that. And finally, what I say is what's really great about this is we can see the example that the quantum computer is powerful. We see that the physics is working right. And as we spend the time and money to build these better quantum computers, these results really supports continued investment, both in money from various organizations and time from scientists. And although we'll have to see if we can build these powerful machines, there's a lot of optimism, and certainly we're far enough along that really strongly motivates everyone working hard to make this happen. So with that, thank you very much for your attention, and I would love to have questions now.